Okay, so today we're talking about the quantum model of the atom. We left off with Bohr's model on Wednesday. So we're finishing by talking about the quantum model. We're going to do more quantum model on Monday too. So let's talk about quantum mechanics. What is it? It's a mathematically based model. So if I haven't talked you into becoming a chem major yet, maybe after today I will. Because if you like math, if math is just your favorite thing, you know, if you really love calculus, then go study quantum mechanics, because differential equations is a prerequisite, or at least it was for me. So it's a mathematically based model. It's based on a wave function, which is, in short, a set of coordinates in three-dimensional space. Now, it's not exact coordinates, right? My coordinates right now would be exact. I can measure my distance from this wall, from kind of the corner right there, from the wall behind me. It's not exact coordinates, but it is a graph in 3 dimensions. And so a specific solution to the wave function, we call that an orbital, right? So if you look at this, this is a general idea of what we're looking at here. 3-dimensional graphs, okay? Now here's the bad news for today. Sorry, it's Friday. I don't like giving bad news on a Friday. But bad news is you don't have the math background to solve the Schrodinger equation yet. Because when I took quantum mechanics, I had to take IFEQ and Calc 3 first. So obviously those aren't prerequisites for this class. So that's the good news, right? We're not going to be solving the Schrodinger equation. We are going to be doing concepts. So it's Friday. Everybody's happy. That's a good reason to be happy, right? So we're going to talk conceptually about the quantum mechanical model. Right, so we know that the electrons aren't in these circular Bohr orbits, right? They're not these perfect little circles. Classical physics doesn't support that. We say, based on what we learned on Wednesday, right, that we can't use classical mechanics to describe the motion of something very, 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 very tiny like an electron. So when we do solve the wave function, we don't get details about the path of the electron. Is that okay? Do we need to know the detailed path of the electron? Does that freak you out? Well, it shouldn't, okay? This is something you've probably heard of before in your other classes, or maybe you've heard people just kind of throwing it around on TV shows. The Heisenberg uncertainty principle: the more accurately we know position, the less accurately we know momentum. So we can know one, but not the other, right? So in classical mechanics, right, studying a car driving down the freeway, you can study both position and momentum accurately, right? Large object. When we're talking about very, 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 very small object, where the wavelength influences its physical behavior greater than its mass does, we can't know both, right? So this was kind of one of the nails in the coffin in terms of, can we apply classical physics to the atomic level? The answer is no, right? It's just not appropriate to use Newtonian type physics to explain quantum level stuff. It's just not appropriate. So this is the analogy I use. You can use a propeller, or even the blades on your ceiling fan, right? If you're laying in your couch this evening looking at the blades, I mean, you have to be really bored to be doing that, but just you know, imagine you don't have anything fun to do on Friday night, right? You know with pretty high confidence that if you are right here, you're not going to get your arm lopped off, right? You're going to be okay. If you're right here, that's not good, right? There's a pretty, really, really, really good chance that that's going to spell a trip to the ER for you, right? We know that the blades are in there somewhere, but we can't point to it and say, yep, there's the blade right there. I have identified it, right? Because by the time I do that, it's already circled 5 times. Probably more than that, right? So this is analogous to the quantum mechanical model and position of electrons. We know the area where it is highly, highly likely that my electron will be, but we don't know its exact position. Is that okay? For us, it is. For me, I don't lose any sleep over it. Maybe you will, but I don't lose any sleep over not knowing the exact coordinate position. It's okay with me. Right? We know our electron is in this region somewhere. We just don't know exactly its position. Right? So the wave function tells us the area where it is most probable that we will find our electron. It's the area where it is most likely that we will find an electron. So this is called a probability distribution. And so we make probability distribution graphs, which are just like when you draw a 2-dimensional graph, right, like a parabola or a line, right? That's a two-dimensional graph. If you make a three-dimensional graph, that would be analogous to a probability distribution graph. So I'll show you two comparisons, graphing in 2D versus graphing in 3D. If you haven't had Calc 3 yet, you probably haven't graphed in 3 dimensions yet. But just imagine the z-axis and taking your graph two-dimensionally and then incorporating that third dimension in there. It takes something planar and makes it, for instance, spherical. So the wave function tells us the region where it is most likely that you will find an electron. You know, it's kind of like playing that Battleship board game, right? You know that the ships are in a certain place based on your guessing, right? If you get a hit, you're like, all right, well, I know that there's another one in this vicinity if I'm trying to, you know, sink one that's got 3 pegs or 2 pegs. Now I've just got to guess, is it horizontal, is it vertical, how is it? This was actually something that I used to have my students do when I taught high school. It's a really common experiment. You may have even done it too. I have my students stand on the floor with a handful of pennies or, you know, bean bags or whatever, handful of something that won't roll. And they would just close their eyes and just drop. And then their partner would measure where the pennies are in relation to them, right? The probability, the greatest probability is that they're all going to be around their feet. And then you'll have some outliers, right, that just roll or bounce or whatever. And this is the same with the electrons in terms of the probability of finding an electron, right? These are the area where it's most likely that we'll find an electron. But are we going to know its exact coordinates? No, that's okay. So here's the difference between a two-dimensional graph, right? That's just a regular old parabola, versus a three-dimensional graph. Okay? So these graphs that we're going to be looking at, these specifically, are three-dimensional graphs of the area where it is most likely that you'll find an electron. Okay, that's where all these funny shapes come from. So if you talked about quantum model in high school and you drew orbitals and you're drawing all these little silly shapes, you're like, why am I doing this? This is so a waste of my time. Well, why are you drawing those goofy little shapes? Because those graphs, those shapes represent graphs. They're three-dimensional graphs of the area where it is most likely that you'll find an electron. Does this make sense? They're solutions to the wave function, and they're graphed in 3 dimensions. So that's where they're coming from. So again, we don't know exact locations. That's okay. Don't let that cause you, you know, cognitive dissonance. It's okay. So we use quantum numbers to describe our funny little shapes. An orbital is the area where it's most likely to find an electron. I think we already defined that term. And an orbital is described by 4 quantum numbers. 4 quantum numbers. So maybe you did this in high school, maybe you didn't. Good news is it's not that difficult. The bad news is there is some stuff you're just going to have to commit to memory. Sorry. Okay. Orbital is described by 4 quantum numbers. The first one we call n, lowercase n. It's the energy level. In other words, it's the size of the orbital. It's the size. Okay? N cannot be 0 because it's the radius. If I say to you, all right, everybody, draw a circle with a radius of 0. Congratulations, you did it, right? Because if there's radius is 0, you didn't draw a circle, right? It's like saying you have a mass of 0. Well, if your mass is 0, then you don't exist, right? If you are an energy level with a radius of 0, then you don't exist. So n cannot be 0. It can be 1 and greater, but it cannot be 0. Cannot be 0, right? Because if you have a radius of 0, then you're not drawing anything. So n is a whole number integer greater than or equal to 1. It can be 1. It's okay to be 1. It just cannot be 0. And this is the size. This is telling us the size. The angular momentum, which we represent with a cursive L, lowercase cursive L. I mean, you don't have to write it in cursive, but I put it in cursive so it doesn't look like the number 1. Right? It's lowercase L is what it is. But I write it in cursive so you don't think it's a number 1. This defines the shape of the orbital. And I'll show you all the shapes in just a minute. I want to get through all the quantum numbers first, and then we'll go back and draw them. Angular momentum, which is lowercase l. Again, I put it in cursive just so that you don't think it's the number 1. It tells us the shape. Now, L can be any number from 0 up to n minus 1. L can be 0. N cannot. Okay? And the allowed range is 0 up to n minus 1. So, for instance, if n equals 4, then L could be any number up to 3, right? N minus 1. So whatever your value of n is, L can be 0 up to n minus 1. So if n and L shouldn't exist unless n is 1, right? Because if n is 1, well, they wouldn't be the same in n either. It'd be 1 and 0. Okay, and we're going to use letters SPDF for the different values of L, and I'll show you what those look like in a few minutes. I just want to get through all the quantum numbers first, then we'll go back in, add the shapes. All right, the magnetic quantum number, which is M sub L, that little L is a subscript. Again, it's just the lowercase L. I put it in print and cursive so you don't think it's the number 1. Okay, it's M sub L, is the orientation in 3D space. So are we oriented along the Y, the X, the Z, or some combination of those? Okay, that's what the magnetic quantum number is telling us. Because we're dealing with 3-dimensional graphs, we have to be oriented along one of the particular axes. So that's where this comes from, the orientation in space. And so here's the range for M sub L. M sub L can be any number from negative L to positive L. So in other words, if L was 3, then M sub L could be negative 3, negative 2, negative 1, 0, 1, 2, 3. Right? It ranges from negative to positive L. Does this make sense? If L is 2, then M sub L could be negative 2, negative 1, 0, 1, 2. Now, right now, I'm just spitting out a whole bunch of numbers that really don't mean anything to you. But after you see and work some examples, it won't just seem like I'm speaking another language. We just want to get through all the definitions first. And I don't have spin on here. We'll do it in a second. Actually, we can do it now. M sub S is the last one. So you can get all of them done. The last one is M sub S. Magnetic spin. That's the 4th quantum number, which is M sub S. And this is spin direction. Is it clockwise or counterclockwise? So that electron is spinning. Is it spinning clockwise or is it spinning counterclockwise? The values are plus or minus 1/2. So that's why magnetic spin's easiest. Because M sub S can only be plus or minus 1/2. Now that is in the slide in a few minutes, but I thought, well, we're talking about all our quantum numbers, let's just talk about it now. So I've got a handout to give you that'll help you keep all these things organized. At least I hope it'll help keep it all organized. And it's on my slide so that you won't have to write it all down. You can just kind of fill in your chart as we go. Marker's getting kind of old. Let's get a fresh one. So we're going to put it all together now. I'm going to have to scoot my table down so I can write on the board. And then I'll move it back up. There we go. Okay, so when L equals, oh, that's right in the way. So when L equals 0, the shape of the orbital that produces is a sphere. Okay? It's a sphere, right? So, now there's only one way you can orient a sphere, right? Just imagine a plain, ball of your choosing. a racquetball, right? It's blue, there are no lines, there are no dots, it's just plain boring blue, right? You can rotate it however many directions you want, it's always gonna look the same, right? There's only one orientation. There's only one way you can orient it. So if you orient it along the X versus the Y versus the Z, it's gonna look the same no matter if you take that racquetball and you rotate it then 90 degrees, 180 degrees, 360 degrees, it's always gonna look the same, right? Because if there are no markings on it, it's gonna look the same no matter. So in other words, does not matter. It'll look the same no matter what. Orient along the X, orient along the Y, orient along the Z, who cares? It's going to look the same. There's only one way you can orient a plane sphere. Does everyone agree with that statement? And the name of that orbital, I forgot to add a row here. Let's just put it right here. The name of that orbital, when L equals 0, that's an S orbital. So just add that to your top column. Forgot to put a row for the name. The name, when L equals 0, is an S orbital. All right, the name when L equals 1, does anyone know? It's a P orbital. And the shape, it depends on how you orient it. It looks like either an 8 or the infinity sign. Right? So it could look like this if it's oriented this way, or it could look like this, or it could be. There are 3 orientations for a P orbital. Right? You can orient it so there's Y oriented, there's Z oriented, and there's X oriented. Right? If you orient it along the Y, it would look like the number 8, right? If you orient it along the Z, it would be kind of diagonal. And if you orient it along the X, it would look like an infinity. So there are 3 orientations to a P orbital. Does that make sense? Orienting it along the Y, orienting it along the Z, orienting it along the X. I'll color those in so they can stand out a little more. But the general shape is 2 lobes, right? It's 2 lobes. And then whether it looks like the figure 8 or the infinity or crooked infinity, depends on which way it's oriented. There are 3 ways you can orient it. Is everybody cool on P? When L equals 2, does anyone know the name of this one? It's D, right? That's the grade you were hoping not to get, right? D orbital, lowercase, okay? Lowercase. Anyone want to guess? Well, I'll show you the general shapes. There are 2 general shapes. 4 of them generally look like a clover, and 1 of them looks like a P orbital with a ring. So if I said draw a D orbital, guess how many orientations there are based on what I just told you here? 4 and 1. There are 5 orientations of a D orbital. Now here's where the drawing gets kind of messy. So I'm not going to make you draw a particular orientation for a D orbital. Okay, so I just want to try to sketch it. I'll show you pictures that are not sketched by me in just a second. But you could have, so 4 of them look like, there's number 5 down here. Okay, so we've got, oops, can't forget the Z-axis. Okay, so we've got 5 ways we can orient. So first one is YZ. So it looks pretty much like what I just drew up here. Now this is where it gets hard to draw. Right, so this is D, Y, Z. And the next one is D, X, Z. So if you imagine it being on this plane right here, it's hard to draw. a three-dimensional object on a planar screen. This is d, x, z. And again, I won't make you draw any specific one. I just say pick a d orbital and draw it. But just so you have an appreciation of these general shapes. Okay, so it's like slicing the board right here. Okay, does everyone see how that works? I'll show you a better picture than my pathetic drawing in just a minute. There's dxz. And then there's dxy. So if it's dxy, this one's flat. It's flat. Okay, so there's dxy, it's flat. I know it's hard to draw. And then there's dx squared minus y squared, which is also kind of flat looking. And then the last one is the dz squared, and this is the one that looks like the p orbital with the hula hoop. Now would I say draw d, y, z, and it better look perfect? No. But I could say draw a d orbital, and then you just pick one of the five. Okay? I won't make you worry about orienting because it's hard to draw. I mean, I have a hard time drawing it, making it look the right orientation and all that good stuff. It's hard to draw a three-dimensional object on a flat piece of paper, right? And then when L equals 3, you have the F orbital. Nobody in here wants to be getting an F orbital, right? And in terms of shape, they are complex. Right? They are complicated. I will not make you draw an F orbital because they are nasty to draw. But there are 7 orientations for an F orbital. So 1, 3, 5, and 7 are your number of orientations. Now notice on the bottom of your chart, so I'm going to move my chart back up so that I can oh, I don't know why it did that. Let's see what that looks like. Hey, that's pretty good. Okay, so we'll erase some of my sketching here. So S, P, D, and F. Number of orientations corresponds to the M sub L values. This is really convenient, right? So if S, remember, L equals 0, L equals 1, L equals 2, L equals 3. Now M sub L, if L equals 0, what is the only value that M sub L could be? 0, right? Look, there's one value of M sub L, there's one orientation. That number of M sub L's corresponds to number of orientations. Isn't that convenient? I think so. Okay, if L equals 1, we're going to have 3 M sub L values. What are they? The range is negative L to positive L. So what were my values for M sub L if L equals 1? Right, negative 1, 0, and positive 1, right? Look, one of them corresponds to this, one corresponds to this, one corresponds to this, right? You had orientation along the X, the Y, and the Z. There you go. If L equals 2, what are the M sub L values? Negative 2, negative 1, 0, 1, 2. And look, that corresponds to our 5 orientations, right? 1, 2, 3, 4, 5. And I erased them, but you've still got them on your page. And then if L equals 3, what are my values here? Negative 3, negative 2, negative 1, 0, 1, 2, 3, right? 1, 2, 3, 4, 5, 6, 7, corresponding to those 7 orientations in 3D space. Isn't that convenient? Yes, it is. Okay, so will I make you draw, for instance, would I say draw a dx squared minus y squared? No, I would not. Would I say draw a d orbital and give me the possible M sub L values? Yes, I could definitely do that. And I'm going to show you a couple other things that are fair game in terms of what I could ask you. But in terms of the content, that's it. That's all the content we're going to do today. Now we're just going to get good at it. Okay, so here are the M sub L and L relationships. Right? You can orient a sphere as many ways as you want. It's always going to look the same. That's why there's only one M sub L. M sub L, that's one orientation, two orientations, three orientations. All right, see, I told you I'd show you some better drawings that are better than my pathetic planar drawings. All right, 5 orientations corresponding to 5 M sub L values. And then here is it in graphical form. Right, if n equals 1, 2, 3, and 4, that's just the size. Now remember, the range for L is up to n minus 1. So if n equals 1, L can only be 0. Right? There's no such thing as a L equals 1 when n equals 1, because the max value of L is n minus 1. N equals 2 gives this option, these options, and these options. Okay, so you got to memorize this right here for sure. At the bare minimum, you need to memorize this. And then you also need to know your ranges, right? What's the range for L? What's the range for N? What's the range for M sub L? So there's S orbital, right? The size, that's value of N in front, so 1s, 2s, 3s. There are P orbitals, right? 2 lobes, orientation, 3. There are D orbitals, get kind of tougher to draw, especially when you have them between planes like those. And then, like I said, I won't ask you to draw F orbitals. They're nasty to draw. They're nasty to represent in general. Okay, so this is a figure from your textbook showing this relationship. What are the allowed values? N, L, M sub L. What are the values for M sub S? There are only 2 values for M sub S. What are they? Positive and negative 1/2. Right. So there's spin. Right. It's only going to be spinning clockwise or counterclockwise. There's only 2 values for spin. So I didn't even put it on your chart because it's easy. All right. So let's talk about how we write this. N is the size. L is the shape. This is the orientation, which I'm not going to get obsessive about how you orient it. Okay? So for instance, if I said it's a 2px, that means n equals 2. And what would L be? If it's a p orbital, what would L be? 1, right. L equals 1. And then this little x would tell you that it's oriented along the x-axis. Right, so when you start taking more like P-Chem, you'll be doing a lot of computer stuff because it just gets too nasty to try to draw this stuff. So those are S orbitals, cross sections. Those are P orbitals. These figures are from your textbook too. Those are D orbitals. Continued. So here's what I want you to do. On your paper, draw a 2P and a 5P, and then show me how they differ. Explain to me how they differ. Now I've here specified to draw it on the Z. So what would a P orbital look like with an n equals 2 versus a P orbital with n equals 5? Well, I did say do it on the Z. All right, so 2P versus 5P. So how would you quantify those differences? Just use tick marks. There's your 2p, right? It has a radius of 2. Yes. And then 1, 2, 3, 4, 5. 3, 4, 5. There'll be your 5p. Right, so the 5p right there. If you want to color one of them in so it stands out. There's your 2p. So what's the difference? They have the same value of L. What's different? They have a different value of N, right? And N equals size, right? Probability of finding an electron is greater in the bigger one. Yes, just like if you're playing darts, probability of hitting the target on a big, huge, gigantic one is a lot higher than if you're hitting a little tiny one. Does everyone see how to draw this and how to quantify it to show one of them's got a different value of N? Now, I'm not asking you to be a grand artist here because, I mean, you've seen how good I am at sketching. So just do your best. That's all I ask. Just do your best. Okay. If N equals 4 and L equals 2, what's its name? So, for instance, that would be a name right there. N and L. So if N is 4 and L equals 2, what's its name? And then draw it. So the first number is really easy. What is it? 4, right? Because that's the value of N. Now you just remember, okay, what letter corresponds to L equals 2? 0, 1, 2, 3, S, P, D, F. So it's what? D, right? So this would be a 4D. Now, if I said draw a 4D, you could have drawn either one of these, because I'm not going to get scrupulous about orientation, for D orbitals especially. So if I said draw me a 4D, and you drew this version, or if you drew this version, I'd accept either one. Okay, we're not going to get obsessive about orientation, especially for D orbitals. We can worry about orientation with P orbitals, because P orbitals are just 2 lobes. Who cares? But it gets kind of hard to draw D orbitals because they're in between axes, and it's hard to draw 3-dimensional objects on a planar sheet of paper. Okay, if N equals 4 and L equals 2, what are the values of M sub L? What do you look at to determine M sub L? Is it N or is it L? You can always remember L is part of M sub L, right? So you look at L. So what are the possible M sub L values if L equals 2? All right, -2 to +2. N has nothing to do with M sub L, right? Because M sub L is the number of orientations, and that comes from what type of orbital you're looking at. Make sense? Make sense? So those are the 5 orientations. Okay, what orbital has N equals 3 and L equals 1? What's its name? You don't have to sketch it, just tell me its name. 3P, right, 3P. We getting the hang of this? How many ways can you orient a 3P orbital? 3 ways, right, 3 ways. You can orient along the X, the Y, or the Z. Because for P, L equals 1. Right, so that means M sub L could be -1, 0, or +1. And each one of those corresponds to a different orientation. Okay, here's one that's going to make you think a little bit. There are 5 sets of quantum numbers. Now we're going to exclude M sub S. We'll include M sub S in the next one. We're going to ignore M sub S for a minute. There are 5 sets that can produce 4D orbital. See if you can figure them out. Now we're excluding M sub S. So think about it. See if you can come up with the 5 sets Now, excluding M sub s, so technically this is not a full set. That can produce a 4D. And if this is kind of stretching your brain in directions that, you know, you don't feel great, I just posted problems on this on the course website in the practice problems folder, and the answer key will be there too. And there are ones on there where I give you a set and say, is this a valid set? And you say yes or no and why. So interpreting those sets will definitely help you get good at this. Because if you can interpret a set, then you definitely know your rules. So let's just do this one together. It's 4D. 4D. Therefore, n equals what? 4. And what does L equal? 0, 1, 2, 3, SPD. So what is it? 2. Therefore, M sub L equals what? -2 to +2. Right? So one of them would be 4 to -2. Right? 4 to -1. 4 to 0. 4 to +1, and 4 to +2. Now, is 3 quantum numbers technically enough? Technically, 3 quantum numbers are not enough. An orbital is defined by 4. So if I said including M sub s, how many sets would you have? For each one of these, you'd have 2, right? 4, 2, -2, +1/2. 4, 2, -2, -1/2. Right? You have to split them up into 2, +1/2, -1/2. Split each one of these up. Do you see how it would be different if we include M sub s? So this is just the answers, I'm pretty sure. Yep. Okay, let's do 3p, and this time we're going to include M sub s. So take a second and get started. I think you can do it. I don't think it's going to be too hard. But I'll give you a second to get a jump start. This is a 3p orbital. So just go through it systematically. You break it down piece by piece. And I really encourage you to go onto the website, to the practice problems folder, and download the practice problems on quantum numbers, especially if this is not something you did in high school. It's not hard, there's no math, but it's just applying sets of rules. And if you've never done that before, it does take a little bit of practice. Just take a little bit of rewiring your brain a little bit. Let's go through this one together. If it's 3p, what is n for all of the sets going to be? 3. And if it's a p orbital, what's L going to be for all the sets? 1, right? And so what is M sub L? -1, 0, and +1, right? And now we have to include M sub s this time. So here we go. We've got 3, 1, -1. Let's just do -1/2 first. 3, 1, -1, +1/2. Right? 3, 1, 0, -1/2. 3, 1, 0, +1/2. 3, 1, 1, -1/2. And 3, 1, 1, +1/2. Do we agree? Starting to get a feel for this? So if I give you a set of 4 numbers and say, is this a valid set? You should be able to look at that set and apply your rules and say, yes, this is valid, no, this is invalid. And like I said, the practice problems online are really going to help you reinforce that skill. I think I've got one more to do. Yes. Okay, if n equals 0 and L equals 1, what do we have? What kind of orbital is that? What? That's right, does not exist, right? N cannot be 0. That's like having a mass of 0 grams, right? I will give you 0 grams of gold today. Congratulations. Okay, what about n equals 2 and L equals 3? What do we have? What orbital is that? Any guesses? 2 what? 2F. This one's a trick question. Why is this a trick question? What's the maximum value of L? N minus 1. The maximum value of L is n minus 1. Right? So if n equals 2, then the max value that L could be is what? 1. Right? That means L can't go greater than n minus 1. So n equals 2 and L equals 3 doesn't exist. There's no such thing. You've exceeded the max value for L. So like I said, there are problems on the problem set that I posted that will go over reinforcing this practice with you. I think that's the last one. Oh, no, that's just the website. It's on the link on the website in the notes as well. So that's where we're going to stop. Hope you have a great weekend, and I'll see you Monday.